All right. Hi, everyone. This is Anna Bergstrom, and we are going to talk right now about acidity in the environment and various sources of natural environmental acidity and some not so natural. And yes, I am wearing the same sweater right now as I am in that picture, in case you didn't notice in previous ones. So, by the end of this video, you should be able to describe different sources of acidity in freshwaters and how they might impact the environment. So, we're going to talk about acidity from the carbon perspective, but now we're going to talk about the organic kind. Previously, when we were talking about the carbonate system, we were talking about entirely inorganic carbon. Now we're going to think about the organic variety. So, organic acids have a huge range of pKa's, and we're going to talk about this in a little bit more detail in a second. But some are strong acids and some are weak acids. There are many common organic acids that you probably already know. Citric acid, what you find in citrus, and acetic acid, that's your common vinegar. And there's many, many more that you probably may have never heard of. So things like benzoic acid or oxalic acid are some other really common organic acids. So why is there such variation in organic carbon acidity? Well, it's mostly a bunch of organic chemistry stuff, and this is not an organic chemistry class, so we're not going to go into it. You're welcome. But what you basically need to know is some of it is the resonance, so how the proton or the hydrogen ion is integrated into the carbon molecule, the electronegativity, so how tightly bound the proton is to functional groups, and orbitals, so what molecule this hydrogen ion is bound to. All of that results in how easily, if you put this organic acid in water, how easily it can pluck off these hydrogen ions and result in excess hydronium ions in your fluid. So these organic acids are very diverse. You'll typically see them divided into two categories. So there are low molecular weight organic acids and high molecular weight organic acids. So basically the smaller in size, lower molecular weight, and the big giant complex one, complex molecules that have a higher molecular weight. So these low molecular weight organic acids are things that you probably recognize a little bit more. So acetic acid, citric acid, they're both low molecular weight organic acids. And these are typically produced by plants and microbes either as, and they can be also a form of organic waste. These tend to be more soluble, again, because they are less complex, lower molecular weight molecules here. And then the way we define a high molecular weight organic acid is one that has more than 3 carboxylic groups. These are typically insoluble in water, and these are typically things like humic and fulvic acid. So you may have heard of humic and fulvic acids before. I'm going the wrong way. And probably the place where you've heard of humic and fulvic acids are places like blackwater rivers. So you'll see this a lot in the Amazon and a lot in the South. You have a lot of acidic soils and a lot of plants going on there, so you end up with a lot of that in the river. These are dark in color, and they result in those blackwater rivers. So these high molecular weight organic acids are typically really poorly characterized. It takes a lot of effort to fully characterize an organic molecule. And so typically you just see them described as things like humic-like, based on how they absorb or emit light or energy. So you typically just will see this and won't actually see any sort of specific organic acid identified. But regardless, it is an acid and it is floating around in the environment, and it does make a difference. So that was the organic side of things, and we're going to move away from carbon and away from the organic side and move into inorganics and things that are not carbon. So one of the biggest sources of acidity in the environment is pyrite, which commonly is known as fool's gold. Pyrite is iron and sulfur, and it is a major source of acidity in the environment. It is common in coal and hard rock mines, and so if you go and dig those up and mine for other things, you end up exposing a lot of pyrite. So if you add oxygen and water to pyrite, you end up with sulfuric acid. So this is a huge issue and a natural source of acidity. So one example of this is the Colorado mineral belt. Again, we have this giant mineral belt, which is rich in a lot of things that people care about: silver, gold, other metals, molybdenum, and along with it is a lot of pyrite. So in the Colorado mineral belt, you can see this is the distribution of abandoned mines in Colorado, and there are just a ton of them. But aside from those abandoned mines, there actually are naturally really acidic streams in here. So this is a recent paper from Garrett Rue, who's at University of Colorado, and we can see is this is up in the mountains here. So this is the Continental Divide. If any of you have skied in Colorado, this is Keystone. I-70 is running along here. This is a basin, and this is Deer Creek. This is the Upper Snake River, and the Snake River eventually flows into the North Fork there. What we have in this branch is the Pennsylvania mine. These sections of stream are colored by pH. So just below the Pennsylvania mine, where a lot of that pyrite was brought to the surface and oxidized and turned into sulfuric acid, we have a pH of that stream water of less than 3. So that is a anthropogenically influenced source of acidity and creating acidic conditions in Peru Creek. However, if you look over here on this other tributary, we can see that we have, without any mines, we have some of these tributaries also have pHs of less than 3, and it's not until they're diluted a little bit that they get between 3 and 4, and eventually, once Deer Creek, which is unaffected by pyrite, you can get a pH to between 4 and 6.5. So these two really low pH tributaries are just because that water was moving through the groundwater with some oxygen in it, it interacted with pyrite, created sulfuric acid, and really lowered the pH of that water naturally. So while mining is a huge source of acidity, it does occur naturally as well. The other anthropogenic side of things that we have now in the environment is acid rain. And while it isn't anywhere near as big of an issue as it was previously, it still is something that everyone should know about. So if we have things like coal, particularly really high sulfur coal, and we put it into our coal-fired power plants and we burn it, we end up putting that sulfur and various forms of nitrogen up into the atmosphere. So this is SOx and NOx is how you'll see it referred to, because it's various levels of oxidized, and that from those coal-burning power plants, once they get into the atmosphere, they're gonna move along and eventually rain out in precipitation. So you get acid rain. Thankfully, Clean Air Act amendments have had a major impact. So the initial Clean Air Act was in 1970. They made an amendment in 1990, so they got a lot better. And we have seen a massive reduction in the amount of acid in our rain. So we can see here that we have massive decreases in acid rain, and it's had ripple effects through the entire ecosystem. So the East Coast, because our coal was primarily coming from the coal country in Kentucky, West Virginia, Ohio, getting put into coal-fired power plants, and downwind of that is the East Coast. If we can see a lot of those effects along the East Coast. So Hubbard Brook Experimental Forest is one of those classic places where we've been studying for quite a while. So we can see here, this is pH in this box, and we can see the pH of our precipitation since 1960 has been gradually recovering, and the pH in the stream water is buffered a little bit, but it is also gradually increasing again. Remember, our the components in our emissions is sulfur and then various other particulates, and we can see that our SOx are declining since the Clean Air Act was put into place. And then in our precipitation, we can see these beautiful declines in sulfate, and which is coming out coming out in precipitation as a result of SOx in the atmosphere. And then similarly, we have this beautiful decline in sulfate in our streams. Similarly, NOx, we have this decline in nitrate in our streams as well. So these classic studies from the East Coast are showing how much of a success story this was when we regulated the emissions from these coal-fired power plants. And so that is the last source of acidity we have to talk about today. And this wraps up our acid base and carbonate module, and we will continue to talk about this in class.